Okay, so I had told you that I did a trick earlier called Baby Hummer that only involved 4 cards, and everybody kind of did their own thing and they followed like a sequence of steps. And in the end, once you kind of followed those steps, everybody should have in theory ended up with the card that they had memorized on the bottom at the beginning, kind of being oppositely oriented to the others. Yes. Okay, this one's slightly trickier than I'm about to do, but you know, we'll see if it works. All right, here I just want to make sure I have the right number of cards. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Yes. So I have 10 through ace. Okay, that's what I have. And this trick is called To Your Heart's Content. Okay. And basically it operates on the same principle that Baby Hummer did. Sometimes this is actually called Big Boy Hummer or Royal Hummer, if you will, okay? But a lot of people call it To Your Heart's Content, and you'll kind of see why. But there's actually an operating principle here in play that that is, it's kind of a combinatorial principle. It's something that's an invariant of the way that cards work. It's very clever. Eventually in the class, I'll kind of explain what's going on, but it's been parlayed into a lot of different tricks. And usually what you would do in this trick is you would have somebody else shuffle these things, okay? They would just shuffle them like crazy, okay? And just do whatever they wanted to their heart's content. You know what I'm saying? Okay. So then what you do as the magician, okay, or mathemagician or what have you, is you kind of go through the cards, okay? And I'm going to do a sequence of kind of flipping some cards over, but I'm going to keep the basic ordering of the deck in play. Okay, so whatever someone did, I'm basically keeping the ordering of the deck in play. In fact, you can do a whole bunch of other things in addition to what I'm going to do and still not mess things up. Okay, this is what is known as an automatic trick. Okay, so like there's a queen and a king. I see these two guys right here. I'm going to actually turn this king over on top of that ace. Okay, there's an ace, there's another ace. I'm going to turn this jack over on top of this king. Okay, I'm going to turn this king over on top of this jack. I'm going to turn this queen over on top of this 10. Okay, there's a 10 and a jack. I'm going to turn this queen over on top of this jack. There's a 10 and a queen of hearts. And I'm going to keep this 10 right on top of that ace like that, okay? So like this is just a big jumble of like things that are flipped and right side up and whatnot. Yes, it's kind of a mess, okay? So if we wanted to, I could go through and I could like give you the option of keeping pairs of cards or 4 cards in the same orientation they currently are, or I could flip them over. I could do all of those sorts of things and still the trick would actually work, okay? Now I'm hoping I didn't mess something up here, but here's essentially what we do now, okay? I'm gonna make a 4x5 row of these cards. There's 20 total, right? So there's gonna be 4 rows and 5 columns. And I'm just gonna put the cards out there and then I'm gonna give you freedom to actually tell me how to fold the cards in to one pile. Does that make sense? And you'll see what I mean here in just a minute. But actually, I could even give you more freedom than that. I could actually ask you, okay, how do you want me to deal these things? As long as I obeyed a few very simple rules, okay? So, but I'm just gonna go ahead and put these out here, okay? So there's the 10, 2, 3, 4, 5. So that's 1 row of 5, okay? I'm gonna make sure I have enough room here, okay? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And I'm starting to run out of room. Move these up a little bit. Okay, you can kind of see what's going on there. 1, 2, 3, 4, 5. Yep. And then 1, 2, 3, 4, 5. Okay. And I'm hoping that this will work so that I won't be hugely embarrassed here. So someone here, so we'll say this is the top, up here, top, the right side of the rectangle, bottom left, top right, bottom left. Okay, so let's just kind of go around the room here. So like Trey, top right, bottom left. Right, okay. 2, 4. Okay, so Ivan, top right, bottom left. Top. Okay. Let's see here, Anna, top right, bottom left. Okay. Okay. Ava, top right, bottom left. Left. Okay. Okay, Colby, top right, bottom left. Okay. And at this point, it starts to become a little bit silly, right? You can't really do top, you can't do bottom. I'm just going to do, you know, right, or I'll let one of you guys pick. So Noah, right or left? All right. Okay, so this would go here. And now it doesn't really matter which way I go, okay? So I'm just going to go like this, like that, okay? Now, I'm really hoping this worked, and I think it may have. So notice, you know, there's a few cards that are flipped over. It'll be amazing if after all that flipping and everything that they were all the same way. But unfortunately, that's not true. There's several cards that are kind of flipped over right now. Do you know what I'm saying? And the other ones are all flipped up, okay? So one thing you can do if you're doing this trick for a group is you can say, uh-oh, well, it would have been amazing if all of these were the same way, but they're not. Oh, well. Well, I wonder what these cards are that actually are down, okay? And you kind of flip them over like this. Queen of Hearts, Ace of Hearts, King of Hearts, 10 of Hearts, Jack of Hearts. Okay, it's kind of interesting, isn't it, right? You guys should all be like, wow, I can't tell because your masks or anything, but yeah. Basically, you have a royal, this is called a royal flush, okay? And it happens to be all the hearts, which is why there's the to your heart's content. Could have done that with any hand at all, actually, and made that thing kind of come to the fore or whatever and reveal itself. But again, this is an automatic trick. It works on the same principle that Baby Hummer did. The reason it's called Royal Hummer is obvious now because that was a royal flush in the end. Yeah, so that's the morning card trick. Okay, and we'll talk about why that actually works at some point in the future. But just wanted to show you that. Cool. I'm going to share my screen here. Okay. All right, so I wanted to mention one last thing with this, but before I do, I just wanted to mention, so today I'm hoping this afternoon, actually, I'm gonna post that test. In fact, I will. I mean, it's basically done. I just have to tweak a couple of things. I'm gonna post the test. And again, you can use any resources that are linked in Canvas, okay? Any resources that are linked in Canvas are fair game. And that thing will be due, what did I say, Monday in class. Now, if you're on the web, you could just take pictures of your exam and upload it. I'll give you the ability to kind of upload that as a file, yeah? And I'll allow it to be like multiple files or whatever, okay? And try to do something standard, not, you know, I think one of the issues I've had in the past is some people have used a particular phone to take pictures and it's kind of made a funny file that I then had to go on the web and convert on my own. So I'd prefer it if it was just one of the standard PIC files, like a JPEG or a PNG or something like that, okay? If possible, if that's the route you decide to go. But if not, you can just print the thing off, write it out, and turn it in on Monday, okay? Make sense? Any questions on that before we get going here? Any questions? And I figured out how to do some stuff here. There's a new, in fact, I can hide this thing too. Hide everything, okay? So I wanted to talk about this because there's kind of an important principle going on here. This was called the truth set of this thing, yes? And we actually did this example down here where we had, so this is the set of x belonging to the integers such that x squared is less than 3, okay? And I could actually write down what this set is explicitly, right? So what is this set? We talked about it last time. So what are the set of integers such that their squares are less than 3? Yeah, -1, 0, and 1. Yeah, that's right. So like this was just kind of a funny way of writing that. Now, in general, you can describe a set, any set, as a truth set. Okay? You can describe any set as a truth set. So let me just kind of write this down. We can describe any set A via truth sets. Okay, and that's actually to our advantage because then basically what we can do is we can turn a set basically into a predicate logic type thing so that we can use all the logic stuff that we learned before. And the way that you do that is like this. You just set, or I better not use the word set because that's going to be confusing. You put A of X equal to the logical statement X belongs to A, okay? So A of X is just going to be the statement X belongs to A, and that's either true or false. Does that make sense? So if somebody hands me an X, I check whether it belongs to A or not. That's either true or false, yes? Okay, then guess what? If I look at the set of X just in the universe such that A of X, okay, the set of all X such that A of X is true, so the set of all X such that X belongs to A, guess what you're going to get back? What's that really just describing? A. Does that make sense? Right, the set of all X such that X belongs to A, hello, that's just going to be A. Yeah, that's like the definition of A, right? So that is, you can take any set and you can correspond with it sort of like a truth set. And the way that you do that is you create this, this little statement right here, okay? In this little open sentence that involves A itself, okay? So this allows you to kind of go back and forth between a set and like a logical statement. And actually, this is really the key for why there are so many things in set theory and in logic that basically look the same. There's a lot of things that look exactly the same, except that you kind of swap out and statements for something we'll discuss today, and you swap out or statements for something that we will discuss today. And you swap out complements of sets, which we'll talk about today, for something in logic, like basically a negation of something, yeah? So it turns out that this right here is there's more to it than meets the eye. Okay, I just kind of wanted to point that out because we're going to move into set operations now. Okay, so let me get out of here and we'll go into set operations. Okay, here we go. Okay, set operations. All right. So first of all, one of the first things we're going to talk about, I mean, we've already kind of been talking about these, but we'll talk more explicitly about Venn diagrams. We'll look at the issue of proving that one set is a subset of another set or that two sets are equal. We'll look at some set identities. And then we'll even talk briefly about, okay, suppose I'm actually writing code. All right. And by the way, you may have noticed, so I mean, Hope Fisher graduated last year. She was a math major, and you know, she took several of the actuarial exams, and she mentioned, hey, you know, because with the QED sent out that email, right? She said, hey, actually, one of the most practical things I learned in college while I was at Cedarville was the kind of learning C++, kind kind of having that be part of my mathematical skill set. Turns out I use that all the time. Not necessarily C++, but just the skills you get from knowing how programming languages work, okay? So one thing that I like to do, and it's been really helpful to me, and I think it'll be helpful to you, is to think about how would I even talk about these things in the context of a computer? How would I communicate a set to a computer in like an effective way? And typically that means you start by kind of going down to the level of zeros and ones or something and try to think about that briefly. And so we'll talk about that at the end of this section, okay? So union. The union of sets A and B, and this is the notation, A, and there's like a little U, B, is the set of all X. Okay, what is this saying? Can someone read this to me? Like what am I saying here? Set of all X such that what? Yeah, oh, well, either one of you guys. That's right, either X is an element of A or is it and? Or, yeah, so this is or X is an element of B, yes? Okay, so X is an element of A or X is an element of B. So if I were to draw a Venn diagram, okay, so there's the universe, and this was A and this was B, okay? Where is A union B in this picture? Not the intersection. Yeah, it would be anything that belongs to either of these, yes? So actually all of this stuff, okay? So even the stuff that they both contain, that would just be the case where it would be true or true, which is true, yes? Okay, so either X is in A, okay, so I could have X's that happen to be here, or X is in B, or both, right? I could have X values that happen to be in the intersection of those two things also, yeah? So that's the union. Any questions on that? Questions? Now, intersection. The intersection of sets, so instead of this, so by the way, let me just mention, notice that this and this look pretty similar. Do you know what I'm saying? The or of logic, of symbolic logic, looks a lot like the union symbol for a union, yeah? And that is by design, okay? Also, it's a U, so it should remind you of union, yeah? That's by design because it's like an or type thing, okay? Now, when I go over here to intersection, what do you notice about these symbols? They look pretty similar, you know what I mean? Yeah? Instead of X being in A or X being in B, I say X is in A and X is in B, okay? So what does the Venn diagram look like in this case? So there's the universe, here's A, here's B. Where is the intersection? It's this kind of overlapping part right here, yes? That is the intersection. If A intersected with B is empty, okay, then A and B are said to be disjoint, okay? So what would the Venn diagram look like in that case? Well, this would be the universe. A would be sitting over here and B would be sitting elsewhere. There would be no overlap whatsoever between the two, yeah? Okay, so that's intersection. Okay, any questions on that? Yeah. Well, yeah, you're right. So in that case, Monique, every X value, like if there was no overlap, every X value for which I check this for, I would get, what would I get for this statement? Since this is an and, I would get, either it's an A but not in B, or in B but not in A. But remember, for an and to be true, both things have to be true. Does that make sense? So you would get false every time. So you would just get false every time, which means how many elements would you have in there? None. Yeah. So there would be no elements in there, which just means it's the empty set. Yeah. You would check that logical statement for every X value and you would get false every time, which just means nothing would qualify to be in the set, i.e. you would get the empty set. Does that make sense? Okay. The difference of sets A and B, which is, there's a couple of ways to write that. You know, you can say A minus B, or you can do this A backslash, right? This is a little backslash B, okay? Okay, is the set of all elements of A that are not in B, okay? Okay, so it's the set of all X such that X is in A and X is not in B, yeah? So what is the set? So I'm basically kicking out from A, I'm kicking out anything that happens to be a member of B. Does that make sense? Okay. So what would the Venn diagram look like in this case? So here's A, here's B. Where is A minus B in this picture? Say again, Trey. Okay, so everything in A, but you kick out that little football-shaped region, essentially, yeah? So shoot, right? And not, it's this stuff right here, but not that stuff that happens to be in B. Yeah?
You also write that as A given not B?
You could say, yes, you can write it as A intersected with the stuff not in B. You could say, this is A intersected with everything outside of B, essentially. Okay? So in other words, this is going to be equal to A intersected with the stuff not in B. And there's actually a notation for that. It's like B bar, okay? Or B complement. And we'll talk about complementation here in just a minute. Does that make sense? So you basically take everything outside of B and you intersect that with A, and you're guaranteed to get the stuff that's in the difference between the two. Okay? But we'll talk about what in the world this complement object is here in just a second. Okay? Like right now. How about now? Okay? The complement of the set A, and there's a couple of notations, A bar or A C. I like to just use bar, as you'll see here as we go along, is the set, it's basically the difference between the universe and A, right? So here's the universe, here's A. Basically, I just take the universe and kick out everything in A, yes? So where is the complement of A? It's all this junk. Yeah, it's everything outside of A. Does that make sense? Okay. So A complement, these are literally equal to each other. A bar is equal to U minus A. Okay. It's the set of all things in the universe that do not belong to A. And now do you guys see why? And let me just kind of draw a picture up here. Do you guys see why? Okay, if this is the universe, and this is A, and this is B, where is B complement? Where is B complement? Isn't it all this stuff? Yeah? That's B complement. Okay, that green stuff is B complement. Yeah? Where is A? Well, we know where A is. A is, let me use yellow for A. A is right here. It's all this stuff, including the intersection stuff, yeah? Okay. But where do those two sets overlap? A and B complement, where do those two things overlap? Certainly, the football-shaped region is not included in B complement, correct? Okay. So what I'm saying is, you know, this yellow stuff right here, this is, oops, let me use yellow for this. This yellow stuff right here, that's A. Okay, and where is A intersected with B complement? Well, it's going to be this stuff right here. Okay, that stuff right there is A intersected with B complement. Yeah? You see it? Okay, because you have the green and the yellow, and you're asking where do those two things overlap? Yes? What do those two things have in common? And it would be the stuff that's in red right here. Okay? Okay, which happens to be the overlap of the green and the yellow. Okay? So in other words, this thing is, we see that this thing is equal to A minus B. It's the same thing that we had for A minus B. Questions on that? Union, what's the corresponding logical connective that corresponds to union? Or, right? It's either in this or in that, or both. What's, okay, intersection, what's the logical connective? And, yeah, and is a logical connective. Complement. What's the logical operation that would correspond to complementation? Not. Right, because here we're saying not in A. Does that make sense? So a set of things that are not in A. Okay, so complementation kind of equates with negating a logical statement. Okay. Why don't you guys work on this for a minute? Draw a Venn diagram that represents this set. So make a universe, make an A, a B, and a C, and you tell me what kind of picture you come up with here. Let me get you started because there's a nice picture that I like to call a Mickey Mouse diagram that kind of represents the generic situation with three sets. There's A, there's B, and C could kind of come in like that. That's why I call it the Mickey Mouse diagram. What does that look like? It looks like Mickey Mouse, right? So A, B, C. So you tell me in that Venn diagram, where is A bar minus the union of B and C? Okay. Okay. Who wants to enlighten us? All right, Ivan?
I'm pretty sure it's everything outside all the circles.
Yeah, okay. So B, okay, you're right. Everything outside of the circle. So B union C, okay? So you take B union C, and you know that B union C, where is B union C? If I had to, isn't it all this stuff right here? Yeah, so there's B union C. But in the end, we want to kick all that stuff out. Does that make sense? Yeah? And where's A bar? Well, that's just everything outside of A, correct? But we also want to get rid of anything in B union C, right? Which in the end just means exactly what Ivan just said, right? It's going to be all this junk out here because that includes everything outside of A, but it also kicks out all the stuff in B union C. Yeah, so everything outside of the circles, that's exactly what it is. So in other words, what have we kind of seen intuitively? What's another way that you could write this? Well, yeah, U minus A union B union C, or another way to write that just notationally would just be A union B union C complement. Does that make sense? Just put a big fat bar over the whole thing. Yeah. Okay, so that would be just the complement of A union B union C. Okay. Okay. Yes.
Can you also use the Morgan's theorem on that? Say A bar.
Yes, actually, we'll talk about De Morgan's law here. So because there's this connection to logic, and a union is really just an or, yes? then when you take the complement of an OR, it's like negating an OR. And yes, De Morgan's law will be something that we will have in our back pocket for sets as well. So what are you saying here then? This is also what?
A bar intersection, B bar intersection, C bar.
That's exactly right. Yes, and that follows from De Morgan, right? This last thing right here is basically De Morgan. De Morgan for sets, but remember, there's this connection between or and union and intersection. Yes, and complementation and negation. That's why De Morgan's law translates over to sets. Okay, that's good. Okay. Great. Proving set equality. Okay. All right, so here are some options. One is that you can use words to show that each set is a subset of the other with an arbitrary element. You can like take an element from the one set and make an argument for why it's also an element of the other set. And then you have to do the same thing in the opposite direction. It's kind of like an if and only if. Remember, I said an if and only if proofs, there's two parts to the proof. There's one that goes the one way and the other way. It's the same thing here. You start with an element in the one set and you show it has to be in the other. And then you start with an element in the second set and show that it has to be in the first. And since you can go from the first set to the second set in either direction, that means they're equal. Something called a membership table, it's kind of like a truth table. A membership table is kind of like a truth table, okay? And you can kind of check the membership table, which is like a truth table, and say, oh, yes, those are definitely the same sets. That is, they have the same membership features here, yeah? Okay. Or you can use known set identities like that involve things like De Morgan's law, for instance, okay? Okay. What about proving that one thing is a subset of another thing? Well, if you want to show that one thing is a subset of another thing, what's going on here is like A is a subset of this guy. Does that make sense? So to prove that that's the case, you have to start with an element in A. So I don't know, X. And you have to show that if you take something from A, where does it also live? In B. And then that's the end of it. Okay. Same thing, you can also do a membership table, although it's a little bit different there. The membership table isn't going to look exactly the same, but everything that's kind of indicated as being in the A set is also going to be over in the B column as well, okay? So everything there is going to also be in B. So the membership table works out nicely in that case. Or works a little bit differently than it did in the case of equality. Okay, let's do A together. Okay, so A, we're supposed to show that A minus B minus C, A minus B in parentheses minus C is a subset of A minus C. Okay. Now, here, look, this proof is going to be really short proof. Okay. Okay, I said that you can either do a membership table or we can just do this in words. I prefer to just write words and kind of think my way through this. If I want to show that the left thing is a subset of the right thing, you start off by saying, take an arbitrary thing in there, okay? So you say, let X be an element of A minus B minus C. Well, what does that mean? That this means what? This means that X is an element of A minus B, and what else? So first of all, that means it's an element of A minus B, and X is, what about C? Is X in C? No, right? And X is not in C. But this means Okay, so think about it. I have x is in A minus B, and x is not in C, right? But what does it mean to be in A minus B? Let's kind of write that out. I'm just kind of breaking it down into smaller pieces right now. What does it mean for x to be in A minus B? Yeah. Yeah, but this means that x is in A and x is not in B. And what else? From before, we already knew that x is not in C. Okay? So think about it. X is in A. Hey, look at this. X is in A, X is not in B, X is not in C. Yeah? All three of those things are true about X. What do we need to be true for X to be in A minus C? For it to be in A and not in C. But isn't that already true? More is true of this element, yes? It's in A and it's not in B and it's not in C, yeah? So it's definitely true that X is in A and X is not in C. So let's just say, thus, we see that X is in A and this X and X not in B, that wasn't very helpful to us, was it? I mean, who cares about that? Okay, and X is not in C, i.e. X is in, what's the definition of being in A minus C? Exactly what we just wrote, yeah? X is in A minus C. And let me just kind of conclude this thing up here. So we conclude, we took an arbitrary element in A minus B minus C, and we showed that that element is in A minus C, correct? Therefore, what do we conclude? So we conclude that what? A minus B minus C is a subset of A minus C, QED. Now, in some sense, what we've done is what I would call universal generalization. We talked about universal generalization. We took a specific element that was arbitrary. We showed that if it's in the one thing, then it's in the other thing, yes? And we said, well, since this was arbitrary, it must be true for any element that happens to be in A minus B minus C, yeah? So what we really just did is something called universal generalization, but yes.
I'm gonna be honest, I didn't follow you at all.
Oh, okay.
Can you show that in a Venn diagram with
Uh-huh.
what you just wrote down with like the circles?
Yeah, right. I would encourage you to understand, I mean, go back and watch it over and over again. I mean, really, it's not too bad. All I'm doing is just following the definition, right? X is in there, but not in there. And then I'm just saying, oh, that just means this. But the picture is like this. Okay, so I don't know, here's A, here's B, here's C, okay? Where is A minus C? It's like right here, right? I mean, I have to avoid the C part, yes, but the B part I could include, but I can't have C in there. Does that make sense? Where is A minus B minus C? So this is A minus C, correct? Where is A minus B minus C? Well, you're just kicking out more stuff. Does that make sense? You're also kicking out the B stuff, yeah? So you're getting rid of that part as well, okay? So do you see that? So that's just this stuff right here, yeah? So you can kind of see in a Venn diagram that's definitely true, yeah? But I would encourage you to try to follow like sort of the argument for why this happens. You're not always, sometimes like to prove that one thing is true of, you know, one thing's a subset of the other, it's not always possible. I mean, it's already getting kind of messed up with the Venn diagram, right? You can imagine if I had like 4 things or 5 things that this picture is going to be a disaster, potentially. Yeah. All right. Any other questions? Okay. Well, why don't you take a couple of minutes and try to explain B, namely, why is it that the difference between A and C, so you can just, if you want to think about it as a Venn diagram, you can. But why is the difference between A and C, A minus C, intersected with C minus B? Why does that have no elements in it? Does that make sense? Why does that have no elements in it? So just think about that with your neighbor together and let me know what you come up with. Okay, so what's the argument? Yeah, we're Joseph.
This statement is a contradiction.
Okay.
Something cannot be not in C and in C at the
Yeah,
same time.
so that's right. So yeah, and here's, yeah, so let's kind of write that down, what you just said formally. So any x belonging to A minus C satisfies X not belonging to what in particular? So what are you thinking? It's not it's not where? In C, yeah? And any X belonging to C minus B satisfies what? X belonging to C. But this is an intersection. And no element X can be in C and not in C simultaneously. Does that make sense? Thus, what's the conclusion? What we did is we said any element, any theoretical element that would be in here would have to be both in C and not in C at the same time. That's stupid. Therefore, what must be true? Yeah, are there any elements in this intersection? No. There's nothing that satisfies. It's kind of like what Monique was saying earlier with, every element would return false in like the truth set of this thing. Yes, it would say false, 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 false every time because it can't be in C and not in C at the same time. QED. Does that make sense? Venn diagram. I don't know. So let's see here. So like A, B, C. Okay, what am I talking about? Where's A minus C? Right there. Okay, where's C minus B? Here. Yeah. So as you can see, there's no overlap between those two, right? You have the green stuff and the red stuff. So something that was in there would have to be both in C and not in C, and in particular inside of A minus C at the same time. Yeah. Yeah, those two things are disjoint. So when you intersect those two things, you get the empty set. That's the definition of disjoint. Yeah. Okay. Okay. Any questions on that? All right. I'll see you guys next Monday. And by the way, if you want to present a week from Friday, please do let me know. Chapter 8 is an interesting foray into the life of the Bernoulli brothers. Okay.